So we'll start the morning session with a talk by Sebastian Pögel, who's currently in Mainz, but will be going up at least in altitude to Zurich. And he'll tell us about Calabi-Yaus and curves in Feynman integrals.
All right, I hope everybody can hear me. It's a great pleasure to open up the last day of this wonderful conference. Thank you very much to the organizers, and I'm very happy to talk about some work that has been kind of continuation to some extent of previous works over the last years, figuring out or looking at properties or geometric properties of Feynman integrals. And in this particular work, we have been looking at the question of whether it is possible to explicitly construct several different geometries that underlie the same Feynman integral. That is kind of the elevator pitch, let's say. And this has been in collaboration with a bunch of people, as you can see here: Hans Jokas, Sören Kodlewski, Puri Kusela, Andrew MacLeod, Mike Sarf, Xing Wang, and Stefan Weinzier. Okay, so let me just start off then, before I go into any more details, just as a brief motivation. So as I think everybody knows, Feynman integrals are, of course, a very interesting class of functions to study, and of course, the main reason that we do it is because they have application in quantum field theory, QCD gravity, and others. And one interesting property that has been known for quite a while now is that in general, these integrals seem to be associated to certain geometries. And in particular, these geometries underlying the integral are determining the function, the space of functions that the final analytic result for the integral will be expressible in. So in the simplest case, where you have kind of a Riemann sphere, you can think of the Riemann sphere being associated to MPL, so just punctures on a Riemann sphere. So these are just generalized polylogarithms. Then what also has been known for quite a while is that there are integrals associated to elliptic curves, and these can be expressed in terms of elliptic integrals, modular forms, generalizations of multiple polylogarithms to elliptic curves. And then the question is, for a while there has been the question what kind of comes beyond elliptics, and so there are quite some things known now. Particularly, what has been studied for quite extensively are integrals associated to Calabi-Yaus geometries. These are kind of the most natural objects that appear. And but also more recently, the interest has kind of shifted to integrals associated not just to also higher genus curves. And interesting function spaces are, well, these are less explored, but for example, there are hyperelliptic MPLs. This is something that has been explored only very recently. The question is, so Siegel modular forms are relevant. These are natural generalization of modular forms. But as you can see here, the question of what function spaces are good to some extent for these beyond elliptic integrals is still a bit of an open problem. Well, not really. I mean, we don't really look at the Riemann sphere as a natural generalization or like downwards, let's say. Well, we focus on Calabi-Yaus because nature tells us that they exist. So because we look at Feynman integrals and we naturally find to the simplest integrals, we find a Calabi-Yaus associated. At least, I mean, so what nature seems to be doing is, like, if you go up a step in complexity from elliptic integrals, at least from the elliptic case, you most naturally find find Calabi-Yaus, which are also the natural generalization of Calabi-Yaus. Since elliptic curves are just well, ignore the sphere. I mean, okay, yeah. Anyway. Yeah, so just as a motivation, just a very quick how-to, how we go about computing some Feynman integrals if you ever stumble across some. So the first thing that you of course do is you just list all integrals that appear, for example, in your process. Then the critical thing is that you don't actually have to evaluate all of them separately, but you can find identities between them. So you integration by parts, you can find symmetries that allow you to obtain a minimal basis of so-called master integrals for your process. Then a very convenient approach that is being used extensively to compute these master integrals is write down a differential equation for them, because they undertaking derivatives, these master integrals are then closed on themselves. Then you have to solve this differential equation. This is where all the magic happens to some extent. And then you obtain an expression for the Laurent series in epsilon. So this middle step here is kind of the most mysterious part. And there are some techniques. And one of the most convenient techniques is if you make an appropriate choice of master integrals. That is another question how you make that choice. To get your differential equation into an epsilon factorized form. So we're taking derivative of the integral is then again a linear differential equation, but with epsilon factorized out, and where A is just a matrix in your external kinematics. And so you want to find the basis of master integrals where A is independent of epsilon, and ideally you would like to understand what kind of kernels appear in this matrix A here. And the reason for this is because once you have the differential equation in this form, you can actually trivially solve this integral to any order in epsilon just through a path ordered exponential. And so in the end, the Laurent coefficients, if you expand this then to any order in epsilon, the coefficients will be path ordered or iterated integrals with kernels determined by A. And so in the end, what the connection will be that the geometry to associate to the integral determines the space of the forms that appear in A. Okay, so now so far we know that geometries play a role, but how do you actually find them? So the simplest, or to some extent the simplest case one can think of, you look at the parametric representation of your integral, you look at the defining U and F polynomials, the semantic polynomials, these generate defined varieties, and you can try to extract the geometry from this. In principle, all the information should be in there, but well, I mean, in principle, everything is in there, but it might be hard to extract. Something that is simpler and particularly very convenient if you use differential equations is if you look at maximal cuts. So you build some kind of skeletonized version of your integral where you replace all the propagators in your integral with delta functions. So you fix some of the loop momenta, and you get kind of a reduced integral with few integrations to carry out. And the nice thing why this is something useful to look at is because this will be the homogeneous solution of your differential equation. So you kind of throw away subsectors, for example, and you kind of kind of zoom into every single sector of integrals that can appear in your problem. And so this kind of allows you to extract this geometry more easily, or much more in a more controlled way. Okay. Now, so as I said before, we know elliptic integrals have been ubiquitous. People have been looking at them for quite a while now. So in this case, an elliptic curve, you can think of an elliptic curve as a complex dimension 1 manifold, and you can also think of it, of course, as a genus 1 curve. And the simplest integral that you can associate to, or that you can find that is that is associated to elliptic curve is the sunrise integral. So where all of these propagators here are massive. But then the question is, how do we generalize from that? And so there are, by looking at various integrals, there are two natural generalizations that appear. First, there's a generalization to high dimensional varieties, in particular Calabi-Yaus. And actually, the generalization here from the sunrise is very simple. You just add more propagators, and for each propagator that you add, you get again a Calabi-Yaus of some higher dimension, essentially. And so this way, you can get arbitrary high dimensional Calabi-Yaus. On the other side, it is also known, though, that there are integrals that are associated to curves of higher genus. And particularly, for example, this non-planar cross box here with internal masses appropriately chosen can be shown to be associated genus 2 hyperelliptic curve. And so this was everything well known. But then the questions that we asked in our project or in this work was whether we can actually build a bridge between these two generalizations. No, there's not a good argument why you would expect just these two classes. They seem to be the simplest classes that you get just by going up in complexity. But I think there's no one saying that, and actually the other way around. I think people are saying that essentially anything that one can imagine can appear essentially at some point. These are the ones, and particularly, for example, and to some extent, for example, these banana integrals here, they are something very natural to appear in a lot of processes because just as a subset sector. So if you just have several massive internal lines and you collapse everything down to this thing, you know your final integral will be dependent on a Calabi-Yaus, for example. So they are kind of natural things that appear quite often. One would expect that there is kind of a constraint on the complexity of geometry that can appear, depending on group order or number of kinematic scales. But I think nobody has actually tried to figure out what that bound is, or have a global scan of everything that can appear. Yeah. Well, yeah, that's what I'm going to get to. So that's the non-trivial part, because they seem very. Well, I'll tell you why. So actually, the question we set out to answer is: can we find actually more than one geometry associated to a specific Feynman integral? And this is not entirely unique. This similar question has been asked by these people here in the context of fishnet diagrams, which are also naturally associated to Calabi-Yaus. And actually, for fishnet diagrams, you can show that fishnet diagrams are, with appropriate propagator powers, are really just periods of Calabi-Yaus. And there was some relation also to Picard varieties. But okay, this is not what I want to get into. So the example that we wanted to work with then was the first non-trivial example where Calabi-Yaus appear. And the first non-trivial Calabi-Yaus is this for-loop banana integral with all equal internal masses. And for simplicity, we look at this kind of skeletonized version to some extent. So we're looking at the max cut because we want to get rid of anything subsector, although the subsectors here are trivial. And we want to look at this thing in d equals 2 exactly. And of course, this thing only depends on a single parameter, z, which we call m squared over p squared. And the typical story is that this is associated to a Calabi-Yaus threefold. This is what you look up banana integrals, and there have been quite a lot of papers on this, that these are Calabi-Yaus threefolds. And particularly, there are different ways that you can find this identification. You can look at the maximal cut and identify this as the maximal cut to be periods, or defining a hypersurface in weighted projective spaces is one way. The other way is you can actually just derive the differential operator that annihilates this integral, which will be a degree 4 operator in Z. And there are actually, for one-dimensional operators, there are a certain class of so-called Calabi-Yaus operators, which are naturally associated to Calabi-Yaus. And you can actually just find this differential operator in lists of these Calabi-Yaus operators. Number 34 in the AESZ list, which is a list made by these people here. And so there are some nice things that you can associate it to with just as context. So generally, we will be working around z equals 0, which is so-called mum point. Not so important what that is. And the other thing is that around the mum point, you can write down a solution space for this differential operator. through the Frobenius method, and you can see that you get one solution which is just a series, second solution which is just log plus series, third is log squared plus log plus series, and so on and so forth. Now the two questions that we then wanted to answer, based on this differential operator, can we find another geometry which has periods that are annihilated by the same operator? This should be L4, sorry. And that's the first question. And secondly, can we actually explicitly construct this geometry? So the plan of action that we are following here. So we start out with this for loop banana integral. We find the typical picture. We find a Calabi-Yaus with an associated Picard-Fuchs operator, high degree differential operator of degree 4. Now, then this is kind of one of the non-trivial steps. We want to perform the matching of geometries on the level of periods. And for that, I will get into that more a little bit later. But for that, we had to define the associated Jacobian variety. And because of our matching procedure, we wanted this to be abelian, because what we want to do is we want to assume that this Jacobian variety is associated, actually stems from a genus 2 curve. And so this is kind of the assumption that we want to make. And from the Jacobian, then we want to kind of go back and, based on the Jacobian, compute the data of an associated curve. And so this way, we are able to construct a genus 2 curve, as it turns out, because for genus 2 curves, the Jacobian of a genus 2 curve has the same shape as this intermediate Jacobian here, whose periods are annihilated by the same operator by construction. And we want to do all of this explicitly. Okay. Well, for some things, yes. For others, it becomes more trivial. I will get to that at the very end, like how well this generalizes and where you would expect might run into trouble. But for Calabi-Yaus threefolds with 1 or 2 parameters, you should be fine. For example, if you go to higher, for genus 2 and genus 3, like if this is a 2x4 or 3x6, well, no, yes, 3x6 exactly. Then it's not restrictive. Then you should always be able to do this. If you go beyond that, you would have to think whether there's actually a curve associated with this because of dimensionality of spaces. I will talk about this at the very end. Yeah. Yeah. Yeah, so this is also still a bit mysterious, because I mean from the as you said, from the U and F, or in this case only F polynomial, you get naturally the Calabi-Yaus, but then how do you actually find some transformation, like some geometric link to the genus 2 curve, is a bit mysterious necessarily. I mean, we do it on the level of periods, and therefore in principle on the level of cohomology. And it is fine, but it would be interesting to understand actually how this works geometrically, for sure. But this is something that we don't understand yet. Yeah. Well, not easily, at least. Okay. So let me just then introduce some things. So let's start on the curve side, because to some extent that is a little bit simpler. Okay, let me just give a quick recap of what an algebraic curve is in the first place. So an algebraic curve in principle is just defined as a polynomial in 2 variables. And you require this polynomial to be 0. This defines a generic algebraic curve. But of course, we want to look at simpler things. So the simplest example that you can think of is that beyond genus 0, I mean, is an elliptic curve, which is just where the polynomial is just y squared minus degree 3 or degree 4 polynomial. And you can show that this is a genus 1 curve, and genus 1 because there's a direct relation between algebraic curves and Riemann surfaces, and so you can associate to a curve then always this kind of topological or genus coming from the Riemann surface. Then we can also look at the next simplest thing, which are hyperelliptic curves, and it turns out that all genus 2 curves are in fact hyperelliptic. And this is just a natural generalization where the polynomial is then just y squared minus some higher degree polynomial. And the degree of the polynomial will determine essentially what the genus of the curve is. And again, you have this kind of map between the Riemann surfaces and curves. So now, as I said before, we want to do a matching on a level of periods. So I have to tell you exactly how you go from a curve to the periods and back again, because in the end, we need kind of both sides. So we want to go first from the curve to what we call tau. This is the reduced period matrix. I will show that in a second. And I will just always limit myself to genus 2 curve because that's the thing that we care about. And in general, a genus 2 curve can be written as some v squared equals a degree 5 polynomial, as I said before. And you can make Möbius transformation essentially to fix 3 of these branch cuts, or 3 of the roots of this polynomial to 0, 1, and infinity. And so you have 3 poles that kind of characterize the curve. You have the period map, which we had heard about earlier this week, where it's just essentially just a pairing between, well, if you want, differential forms and contours, or the Ram and Betti the Ram cohomology and Betti homology. But in the end, it's really just integrating certain differential forms over certain contours. And for example, especially for a genus 2 curve, you have a basis of holomorphic forms, which is just du over v. So the v is where v is just the square root of this polynomial here, and u du over v. And then based on these on these roots here of the curve, you can define some cycles, some A and B cycles, which have nice intersections, so they're kind of orthogonal. So these are symplectic bases of contours, and this kind of allows you to get a symplectic basis for your periods. From this, you then build the so-called period matrix. So this is just essentially all the differential 1 forms integrated over all the cycles. So it's a 2x4 matrix. And then you can just row reduce if you want to get kind of the reduced period matrix, which in general you just call tau. And the way to think about this is, and the picture that you usually have from the elliptic case is that you have a lattice spanned by 1 and tau. And this is just the higher genus generalization of this. So whereas before you had tau living in the complex upper half plane, you now have something called Siegel upper half space, where this matrix tau now has to be symmetric, and the imaginary part of this matrix has to be positive definite. This is kind of the natural generalization of this. And if you look at essentially this thing here, as I said before, this generates a lattice. And this lattice is called the Jacobian variety, and is also a complex torus, just as in the elliptic case. And actually, you can find that you can always find that that if tau lives in a Siegel upper half space, then this Jacobian is an abelian variety. So this is an important property that we will need for later. And this is true for any curve. Then let me go back the other way. Now let's say you have a tau and you want to go back to your curve, which is something less trivial to some extent. This is in fact possible. So you start again with your curve, let's say. You assume you have a curve like something like this. And you're given a tau. So you can actually get these branch points E2, E3, E4 just from ratios of theta functions, where theta functions are well, these are the typically Jacobi theta functions. You can just generalize them to higher genus. Not so important what they are, but the fact is you can do it. And secondly, you can actually get the full period matrix, because in principle, this tau is the reduced period matrix, but you would like the full one. But in fact, you can also get just a full period matrix in terms of theta functions. Okay, so this is essentially the curve side of things. Then let me talk about Calabi-Yaus side. Sorry, the Teichmüller space or the moduli space? Yes. So I mean, anything is related to the so the periods are like if you work with symplectic bases, then symplectic periods then usually have relations with symplectic transformations, right? Yeah. In principle, you can. This depending on which theta function you choose, you get a certain version, but then you can still always find symplectic transformations. In principle, there should be another construction with theta functions, but we just pick one that you like, essentially. Okay, so on the Calabi-Yaus side of things, let me just review some quick facts about Calabi-Yaus if you hadn't seen them before. So at the case in the case that we're looking at is we are looking at a one parameter family of Calabi-Yaus threefolds. So one parameter because we have only one parameter z. And a property of Calabi-Yaus is that in this case, then you have a unique holomorphic free form living in this H3Z. So this is essentially all the holomorphic free forms, exactly, and it's just spanned by a single unique form. You can look at the cohomology more generally. You can look at all the cohomology groups that you can associate it to it. So not just the H30, but also mixed groups. And so this is usually kind of summarized in the Hodge diamond. Essentially, just tells you what the dimensions are of these spaces. And typically for our we are mainly concerned with this middle cohomology essentially. And so, for example, is H30. So first of all, this thing is symmetric, do complex conjugation. And so H30 is equal to H303, which is 1, since we know that these three forms are spanned just by a single top form. And then yet another thing that you can say is that H21 and H12 are equal to M, where M is the number of so-called complex structure moduli. And with these, you can just think of them as essentially, to some extent, the number of parameters in your Feynman integral. In this case, M equals 1, because you only have the one variable z. Okay. Equally, as for the curve side, you can define periods of the Calabi-Yaus. So again, you have a period map, obviously. Mapping so between the differential three forms and three cycles. And yeah, matching as equally the same as before. But you can do better. So there are some specific so-called integral periods that are important. So first of all, you would like your integration, your three cycles to be integral cycles. So as before in the curve case, it was simple because you had the symplectic basis with where the contours were just encircling the branch cuts, for example, and you want essentially the higher dimensional equivalent of that, which is actually not trivial to find. Yeah, sure. Mm-hmm. Yeah. So if you have the most general for loop banana integral, so in this case you have 5 parameters, right? You have for each mass you have 1 parameter. Then this would be 1, 5, 5, 1, for example. Yeah. Yeah, so this is true. That you have to look in principle, like if you want to go from the 5 parameter case to the 1 parameter case, you actually look at a quotient. So you don't just specialize to Yeah. So this is kind of, I just glossed over that because, but yeah. So there's some sub-hot structure essentially, which is then the equal mass case essentially. Okay, yeah. So again, as I said, integral periods. Opala. So again, you want to, first of all, you want integral cycles, and what the other thing is, you would like to specify just you would like to integrate over this unique three form that I was telling you before. And if you can, again, just in the curve case, you can find a symplectic basis of these cycles here using mirror symmetry, if you care to know about that, but I don't want to go into that right now. And essentially what you can then write down is you can find a very nice representation of your period vector, of these integral periods. So these are integrals over this top form. And you can actually express these periods in terms of this Frobenius spaces that I was telling at the mum point. So there are very compact expressions for these in terms of these Frobenius spaces, and also some topological data which comes from mirror symmetry. Again, not so important. Okay, so we have periods, great. But as you will notice, this is just this is essentially just integrated over a single differential form. But to do the matching with the curve side, we want two forms. So we have to figure out what's the other thing that we want to integrate over. And this is related to then the story, something that's called intermediate Jacobians. And you can think of this as the natural generalization of this Jacobian variety, where in the curve case, to high-dimensional, high-dimensional varieties. Because things are not so trivial at this point anymore, and particularly you have choices, which can be nice and can also make your life hard. So in general, if you want to look at the Calabi-Yaus threefold again that we are looking at, such an intermediate Jacobi is in general defined as you take your differential three forms over C, mod out by the differential three forms over Z, over the integers, and you add some complex structure. So this is kind of the, doesn't play a role in the curve case, so but for high dimensional varieties, this does play a role. And what I mean with complex structure is essentially you have to pick some half-dimensional subspace of H3 over C. So essentially this dimension of V, so this dimensional is just one half of the dimension of the entire three-dimensional three cohomology, such that V and the complex conjugate of V generate the entire space again. So this is essentially just, you have to figure out what the complex conjugation does to you. And so in general, an intermediate Jacobian will be defined essentially by so the differential, all differential three forms modded out by this half-dimensional subspace and all integers, integer multiples of differential three forms. And as you can show, that this actually generates again a complex torus as you would like. And in principle, and equally, you can actually compute this complex torus explicitly if you have some generators for this half space. And you can also check that this is actually the case, that this is actually a complex torus, because this thing is a complex dimension 2m+1, and each of these spaces separately has real dimension, I mean, and each of these spaces separately has dimension m+1. So you can see that this kind of makes sense as a complex torus. And again, with complex torus, I mean literally just this generalization of in the elliptic case, where you have some normalization, where you have a tau parameter in 1, and essentially you want a generalization of that. Okay, so now we have intermediate Jacobians, but now we have to make a choice because we want to figure out what complex structure we have to use. And there are two classic choices for this. First, the so-called Griffiths intermediate Jacobian, and this is essentially if you pick as this half-dimensional space, you pick these two cohomology groups, H30 and H21, and this has some nice properties. First of all, the main property that you like actually is that these two taken together vary holomorphically with Z. So essentially, because your Feynman integral in the end should just depend on Z and not on Z bar. So this is kind of something that you want to represent also in the choices that you make. So this is good. Unfortunately, it is very clear, and one can prove that the complex torus defined if you make this choice V is actually not, that doesn't actually define an abelian variety. So this is no good, because in the end, for this matching to genus 2 curves, you want to have an abelian variety. Then there's a second choice that one can typically make. So this is essentially if you take the subspace H30 and H12, so you just skip this one here. And this is a good choice in some sense, because actually you can show that it does define an abelian variety in the end. However, you lose the nice holomorphic property that you had here. So this thing, actually, these two together will actually not vary holomorphically with respect to Z. So this is kind of the downside. So neither of these actually work for us, because first of all, to match to a curve, we want first of all an abelian variety, and due to us having to deal with a Feynman integral, we only want Z and not Z bar to appear. So kind of as a solution, we just make our own, sort of, which enforces these two properties. Sorry? Well, this is kind of the idea. 1 second. So the idea is essentially you pick a suitable real region in this complex structure moduli space. So for example, in this case, 0 to 1/25, where this is just the threshold of the banana integral. You start from the Weil intermediate Jacobian, which has this abelian property that you wanted. And you assume that you are always working in this real subslice. So you just always assume that Z is real, because that's what in the end what you want. This is always true here. So every time that you encounter a Z bar, you kind of replace it with a Z. And then you holomorphically continue from that. So on this real subslice, it will match, but you actually, once you go beyond there's a small tubular neighborhood around this real subslice where you still have a valid intermediate Jacobian. It won't be the Weil anymore. It won't be any of the classical ones. It will be some fun linear combination of things. But in the end, you don't care. You just want to do the matching of the periods in the end. Okay, so how does this actually work? So you define essentially what we call the holomorphic intermediate Jacobian, which is essentially this means the Weil intermediate Jacobian limited to the real subsplice. So the nice properties then are essentially that this is manifestly holomorphic, as you would like, because you have kind of enforced it by hand. And it is manifestly abelian, because that's kind of what you, well, at least on the real subslices, that manifestly abelian, because there's just a Weil intermediate Jacobian. But then you have to figure out actually how much, what is the extent of the validity of this abelianness, essentially. And for this, you can just essentially look at the lowest eigenvalue of the imaginary part of this Jacobian, and see once it becomes 0, essentially. And you can do this, and you can just plot the smallest eigenvalue. So you just test this positive definiteness of the imaginary part, and you can actually find that actually it extends quite far. So within essentially this entire blue region, you have a valid Jacobian associated to your Calabi-Yaus, which is holomorphic in Z, and which defines an abelian variety. And the other thing I want to show is that all of this is not just something hand-wavy, but you can actually, with some technology that I haven't shown you, but in principle you can do it, you can actually evaluate all of these things explicitly with high precision numerically. Okay, so as a summary, we have the following correspondence now. So now we can actually construct a so-called, to some extent, a curve associated with Calabi-Yaus. So we start from the Calabi-Yaus. We define this holomorphic intermediate Jacobian. We assume that this is essentially just the Jacobian of some genus 2 curve, and we can actually recover the curve from this. And we have done this, and not only do we have a curve, but even more, we actually are able to explicitly construct a differential one form for this curve, such that this differential one form integrated over cycles defined by the curve gives you the same periods as the Calabi-Yaus did, essentially. So really, what we have is we have differential one forms or periods of a genus 2 curve that are annihilated by the same differential operator as from the Calabi-Yaus side. And so this is something we dub a Calabi-Yaus curve correspondence. Right. Okay. So now then to your question, how often, or like what are kind of limitations on this kind of construction, particularly if you go to higher dimensional Calabi-Yaus or if you add more moduli, more parameters. And this in some extent is not obvious. And this is related to something called a Schottky problem, which is a very classical problem in algebraic geometry. So for algebraic curves, the Jacobian is a map from the moduli space of genus G curves to the space of abelian varieties. So this means that for each curve you can find an abelian variety. However, the reverse is not necessarily true. Not for every abelian variety you will find a curve. So this is kind of non-trivial that this should be possible. And this is known as a Schottky problem, as I said. And so you can just compare dimensions of these two spaces. So the space of the modular space of genus G curves and of the space of abelian varieties. And actually what you can find is that for genus G curves, it's 3G minus 3. For abelian varieties, it's 1/2 G plus 1. And actually for genus 2 and genus 3, these two dimensions are the same. So you will always be able to find essentially a direct correspondence between curve and so between abelian varieties and curve, and thus thus you will be able to construct periods from the Calabi-Yaus. You will find a genus 2 curve, which is annihilated by the same differential operator as the Calabi-Yaus. However, for generic Calabi-Yaus, this is of course not obvious. So this will only be the case. So genus 2 and genus 3 will be realized, for example, in the Calabi-Yaus threefold case, if you have one or two complex structure moduli, so one or two parameters. So for example, if you exactly. But if you actually go beyond that, there has to be something non-trivial happening for this to work. So essentially, then you actually have to test whether this intermediate Jacobian that you have just constructed actually lies what you can call the Schottky locus, so the space of abelian varieties that define curves. And this is the non-trivial part. And so far, we don't know whether this always will be the case for Feynman integrals, or whether this in general, this is something interesting to look into actually. Yes, in the end, but okay, once you at least for the threefolds, then there's some relation. Right? In principle, the higher dimensional your Calabi-Yaus is, the bigger your cohomology is going to be to some extent. Depends, but I agree. So for now, we're just limiting ourselves to Calabi-Yaus threefolds. Okay, then let me just wrap up. So the problem we set out to was to test relations between the geometries associated to Feynman integrals. So we assumed kind of that the differential operator that denies an integral is something fundamental, and particularly the interpretation as the annihilator of periods of the geometry. So we then looked at the easiest Calabi-Yaus example, or non-trivial Calabi-Yaus example that we can think of, the for-loop banana integral at equal mass. We performed a matching of periods at the level of intermediate Jacobians. This way, in certain regions of the parameter space, we were able to essentially find an exact correspondence between Calabi-Yaus and a genus 2 curve. And to do this, we needed to construct a new holomorphic intermediate Jacobian that satisfies all the properties that we wanted. Now, of course, there are some natural generalizations I can look at and a lot of open questions. So you can obviously go beyond the maximal cut. So if you go beyond the maximal cut, you also have subtopologies. And if you go also beyond d equals 2, in principle, you would expect, the question is, for example, whether you can use this hyperelliptic picture or this genus 2 curve picture to express this banana integral in certain ranges of parameter space in terms of, for example, hyperelliptic polylogs associated to this curve. Since for Calabi-Yaus, good function spaces are not really known. You can go beyond one parameter. So you can, for example, relax the equal mass condition and add more parameters and see what happens. But particularly, we would expect, at least for 2-parameter case, this still to work. Once you go beyond, who knows? You can go beyond a single kinematic patch. In principle, we did this matching on one real kinematic slice, but in principle, you're free to also choose different slices. And then the question is, what are the relations between the curves that you get between different patches, essentially, or between different kinematic slices? And you can actually also go beyond Calabi-Yaus threefolds, as you said. Yeah. But more broadly, I think what is the much more interesting question is kind of to try to identify the relations, more generally identify the relations between geometries, and use these kind of identities to kind of pick the one that is best suited to the problem that you're looking at, and try to understand better exactly what the role of these geometries is in quantum field theory. Okay, thank you.
Do we have any questions? We're already a number, but I guess we can allow you to have.
Sure. I think I lost the idea somewhere. Is it that you don't know how to evaluate these multi-loop banana integrals, and you're hoping by relating them to some simpler integrals or simpler curves, you can learn something about these functions? Or?
Well, I mean, so we are able to evaluate them, but well, so let me phrase it like this: for elliptic, for GP, like MPLs or elliptic polylogarithms, or now these hyperelliptic polylogarithms, these are nice function spaces with well-defined properties that people understand, or mathematicians at least understand very well. So you have some closure under integration, for example. You have some nice properties. For Calabi-Yaus, this doesn't really exist. So we do have techniques to evaluate them, particularly, for example, banana integrals, but also cases where banana integrals appear as subsectors. But maybe to some extent, these are not so much understood. So we get periods appearing in these differential equation kernels. You get periods, you get iterated integrals of periods, and they all look kind of random, and there's no way to it's not understood how to classify any of this. So in the end, this is enough to evaluate, because then you can just do series expansions and you still get a result. But ideally, morally, you would like to go beyond just being to evaluate them.
So the other obvious question is, can you go the other way if I give you a hyperelliptic curve?
Well, that's that's kind of the equivalent of this kind of shot problem, but the other way around. So what the Abelian varieties kind of define are intermediate Jacobians of Calabi-Yaus. I think that is not known. So I don't know.
Can I ask a question? Oh, the inverse problem is known to be a quite deep problem. This is all very cool and cool looking, but I just wonder, I take it there's one example with this banana graph, and when you get the periods in terms of the genus 2 curve, I mean, do they look good? Are they related to the graph? Do they make you hopeful that this is going to lead to some general story? What's
so one thing, okay, we don't have explicit, so let me say it like this. We can do series expansions for example, if you want to make this matching and you want to look at, for example, the curve polynomial or its roots. We know that these we can do series expansions for these for these roots, and we see that they're not just simple series, but well, we can show essentially that these are not going to be rational functions of the external kinematics. That we can show. Because we can compute the invariance of the genus 2 curves, Gusa invariance, for example, and one knows that if there's a rational dependence of the roots on the external kinematics, on your parameters, then also the Gusa invariants have to be rational functions in these parameters. So since we can see that this is not the case. We have some proof essentially that we know that they're not rational functions. We know that the roots, for example, are going to be transcendental functions. What exactly they are, we don't know yet, but we can compute everything in principle up to in series expansion. But I think it's maybe a little bit too early to kind of say exactly how much use there will be in this, because I think this is just the first example where something like this was explicitly constructed. And as I said before, there are also other examples in case of these fishnet graphs, for example, where people have very explicit relations between different geometries. So I think there's more to be understood there, and also from the practical point of view. Yeah.
Are there any other questions, Yang? Just a second.
I have a naive question. So thanks first for this very beautiful story of this hyperelliptic curves. But do you have some Feynman integrals which are associated with some kind of high genus algebraic curve, which is not hyperelliptic? Is that an example like this?
Which is not hyperelliptic. I don't know of any, because the way you usually identify it, for example, with the maximal cut, with Bykov,
it's just one square root. It's not a
exactly.
Root.
So it would be interesting to see how one can generate anything else than y squared equals something, essentially from Feynman integrals from Bykov, let's say. Yeah, that's I think so. Long story short, I think no, I don't know any that are not hyperelliptic necessarily.
Thank you.
Any other? Ah, yes, Lionel.
Hi, just I mean, can you understand this relationship with curve by some kind of elliptic fibration or something, or is that I mean, if it's just a two-dimensional Calabi-Yaus, there's a big story about elliptic fibration,
right?
And,
right.
So you can imagine just doing the integrals over the fibers first, and so on and so on.
We have a more geometric understanding of the relation between these geometries. We do not. I mean, we don't really understand how you go from one to the other. There should be a map somehow, but what that actually is we have not figured it out. Yeah.
Anyone else? All right, if not, let's thank Sebastian again